All right. All right, so I guess we'll get started. My name is Robert DiGiovanni. I'm the instructor for this course. I recognize several of you, and there's a lot of faces I don't recognize. So anyways, welcome to Calculus 2. I'm hoping that all of you have had an opportunity to get into Canvas and take a look at our course. Does anybody not know at all how to navigate to Canvas and to get into their courses? Anybody? If you do not, okay, please just talk to me after class. I'll help you get in there. If you click on your courses, it should bring up the wrong semester. Oh, it actually brought up the right semester. How about that? Normally this does not bring up spring 2017, usually it brings up fall 2015 for me. And this is my teaching schedule. You'll have your schedule in there. I'm teaching one college algebra class, 3 Cal 2s, 1 Cal 1, and 1 Cal 3. 3 of those are online courses, but I have 2 face-to-face Cal 2s. You are my second one. My first one meets at 9 a.m. on Tuesday, Thursday. So just FYI, you're one of 2 face-to-face Cal 2 classes I have. So your section is section 24, and you'll click on that to get here. And your screen will look something like this. You probably won't have this stuff over here on the side. But the most important thing here is for you to watch this orientation video. And I don't remember how long it is. Shall we see? Ooh, wow, an hour? Oh, wait, that's linked to the wrong, wait a minute, hold on. Hold on. This is not right, hold on. Did that take me to the right course? Come on. Oh, I went to the wrong class, that's why. That was my internet. You're section 15. Let me double check that here. Yep, section 15. I'm sorry. But you still have an orientation video, okay? But this is for you all. And this one's 30 minutes long. There you go. All right, so I expect that you're going to watch this video. And it's me basically going through the syllabus, going through the Canvas page, showing you where things are, where you can find the notes that I'm going to follow in class. They're all provided for you online. The schedule, you know, what I'm going to do every day, when your tests are going to occur, things like that. And then there's a link to your class lecture videos, which is this camera here. I'm going to record every lecture, and so you'll pretty much see everything that's up here. And I actually just recorded the one this morning, so I'll just give you an idea of what it'll look like. Might be loud. Hold on. Yeah, that is the orientation video. Why did I click on that? I meant to go right here. So this is my 9 a.m. class, and this was today. So I already uploaded their video from this morning, and come on, you can do it. So that's pretty much what you'll see. This is not a very good projector, but so this is what you'll see. And for those of you who are interested, I'm going to record at 720p, 30 frames per second. So it's not super high quality, but good enough that you can see what's going on. It just keeps my file sizes smaller. And so you'll have a playlist that you can go to, and I'll organize it by, like I'm just naming it Tuesday, Thursday, 9 a.m. It'll be 3 p.m. for you. What day it was, so today will be day 1, and what section we covered. So that's the way I'm going to organize it. And feel free to add me to your, like you can subscribe. I'm not asking for people to subscribe or anything, but you can if you want. And then anytime new videos pop up, you should get a notification. So, all right, that makes sense? All right, and then all of the homework assignments that I assign for you, will come out of the book, which we use this book. You probably used it for Cal 1 if you took Cal 1 here. All the problems will come out of this book, and I have already worked out all the problems that I assigned for you on video, and so you can click on that and you can watch me working through the problems. The idea on that is that you would sit there and try and work the problem yourself, and maybe kind of watch the video, pause it, and just kind of make sure we're both going about the same way. I don't recommend that you just, the day before the test, watch all my homework solution videos, you know, with popcorn and drink and expect that you're going to understand it all right? You got to get your hands dirty. So, but they're there for you, so hopefully you won't ever get stuck. I have had students tell me that, you know, the class lecture videos are useful, but that the homework solution videos were the most useful for them. So hopefully you'll find the same. We'll see. All right, so you do have a first assignment that is due. It's due at 6 p.m. We're going to finish up here about 4:40, rounded up to about 5 o'clock. Your first assignment is due on Thursday, 6 p.m. You have to click right here. It's a yes or no question about the syllabus and about the orientation video, and that you've watched and that you understand the requirements of the course. So that's like you signing off on the syllabus, and that way if you ever come back and you're like, well, I didn't realize that exam 2 was worth this much, and I'll say, well, you said you did, right? So this is my way of having some evidence that you know what's up. Any questions? No? Okay. So again, I'm not going to take time to discuss any more here. I'll let you watch the orientation video. All right, that's it. Thanks for coming today. I'll see you all on, no. Y'all ready to get started? Okay, so let's do a quick recap of Cal 1. And just what I mean by that is we're just going to have a discussion about what were the important concepts in Cal 1. I'll try and point out the things that I think you'll need to be very, very clear on. I'll even go back to pre-Cal and talk about some of the things there. I'll give you a brief introduction into Cal 2, and then we'll get started with today's notes. We're going to cover 3-5 or 3.5 out of the book, which is inverse trigonometric functions. All right, so first, let's go back. Cal 1. So what was that about? Okay, derivatives, limits, I'll put those down in the order that they appeared. All right, so the limit was the heart of calculus. I mean, that's the most important part of all of calculus is the limit. From the limit, we create this idea, this definition of the derivative. And what else? Okay, so integrals, that would be towards the latter end of Cal 1. That's, I'll just put antiderivatives. That's where we're going to pick up. How many of you saw antiderivatives in Cal 1? Okay, now this would probably be a very, very simple introduction to it, like the antiderivative of cosine would be sine, because the derivative of sine is cosine. And the antiderivative of x squared is 1/3 x cubed plus c something. Okay, whatever. So you maybe saw some basic things like that, all right? So this is in Cal 1, but by no means was it covered thoroughly, all right? So I'll circle it. What else in Cal 1? Anything that you can think of. What? I'm sorry, what? Related rates. You know, my other class, my 9am, nobody mentioned that. I think they were all suppressing it. Related rates. Those are those word problems. Those are the ones like, you know, a spherical balloon is, you know, growing such that its surface area is increasing at a constant rate, and blah, blah, blah. How fast is the radius increasing when the surface area is blah, 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 right? That's related rates. To do related rate problems, you had to be able to do a certain type of differentiation. You know, you remember? Implicit differentiation. So within derivatives, there was this idea of implicit differentiation, and that's when you couldn't solve for y, or if you had more variables in there and you wanted to take the derivative with respect to some other variable like time, then we would use implicit differentiation. What else in derivatives? There were some core concepts with derivatives. Pardon?
Continuity.
Okay, continuity was a property of functions. I'll put that in here, continuity. Continuity.
Figure out the change in the function at a certain time.
Okay.
Tangent line.
Tangent line. Okay, so geometrically, if you want to talk more about derivatives, if you want to look at it geometrically, we had some function f, right? And if you take some point, I'll call it x, then you come up here, and f prime of x then would represent the slope, right? The slope of this line, this tangent line. That's what the derivative represented geometrically. And that helped us because we were able to use this idea to figure out highest and lowest points on graphs by trying to figure out maybe where the tangent line was 0. So we'd like set the derivative equal to 0. And then we'd also figure out where it's undefined and things like that. Okay? Good. Anything else?
Differentiation.
Logarithmic differentiation. Good. That was a type of differentiation we could do. Logarithmic. I can't get that thing to stop popping up here. All right. When it came to derivatives, there were those, you had to do all derivatives with limits first, right? And then at some point they gave you these rules, and you were very happy about that, right? So you have, like, what were the rules? Power rule, product rule, quotient rule, chain rule. That's the order in which you saw them. So of those rules, product rule, quotient rule, chain rule, power rule, all that, the rules, the most important one is the chain rule. Now you can't do chain rule without all the others. I'm not saying the others are not important, but in this class, the chain rule is huge. And the reason why is because we are going to be doing antiderivatives, which requires us to go backwards. So it's the reverse process of differentiation. And we saw that in Cal 1, when you had chain rule, you would start with something that would look pretty simple, but when you took the derivative after the chain rule, it would look very complicated. So if we're trying to go backwards, we have to be able to see patterns. We have to kind of see that what we're looking at is the derivative of something after chain rule has been applied. And so the better you are at chain rule, the easier this is going to be. If chain rule is, this thing that, well, you got through Cal 1, you did well enough on everything else, but you never understood chain rule, that's going to come back to haunt you in this class. So we want to make sure everyone tightens up all their knowledge of these rules, specifically chain rule. Okay? Anything else? Max and min. So let's tie that into like curve sketching. When we did curve sketching, we could find max and mins. You can find max and mins on closed intervals. You could find max and mins on open intervals. There were two different methods. And that was all tied into a topic, an application of optimization. The farmer with the fence and all that stuff, right? So optimization, max mins, that could all fall into a different category, but they all branch off from the derivative, and the derivative branches off from the limit, right? Okay, that's Cal 1 in a nutshell. I think what you need to know, just for now, the most important thing is your rules of differentiation. So Cal 1 is referred to as differential calculus. Differential calculus. Cal 2 is called integral calculus. And it's called integral calculus because we do the opposite of differentiation, which is called integration. But again, we'll formally introduce all of that in a little bit, or as the semester progresses. So let's discuss Cal 2. Here, I'll just change that to a 2 there. So in Cal 2, we have the antiderivative, all right? And the antiderivative, we're going to spend about a third of the semester on trying to be able to find antiderivatives of functions. In fact, it starts really next Tuesday is when we start antiderivatives. And I actually like to introduce antiderivatives as if you've never seen it, because I know that there are some students who don't get really a good treatment of it at the end of Cal 1, so I'm going to treat it like you've never seen it. If you have, don't be like, yeah, man, I'm all good. I don't have to really pay attention, because it's going to be quick. And as soon as that's over, we get into it. Then the Thursday after that, We get into substitution, and then after that, the following week, we start what we call the techniques of integration, and that's going to carry us all the way through to March 7th. So all the way up to the second exam before spring break, we're going to be doing integration, right? Antiderivatives. That's a huge part of the course. And then we're going to move into applications. So, you know, with derivatives, we just give you the rules, right? Like here's the power rule, product rule, quotient rule, chain rule. And once you understand the rules, you can pretty much take the derivative of anything. I mean, theoretically, somebody gives you a function, you should be able to kind of like break it apart and look at it and say, ah, that's a product, but there I've got a chain. And so it's a very mechanical process. The antiderivatives is not as mechanical, all right? Again, you have to see patterns, you have to recognize things, and it's not as simple as, I'm just going to do derivative of this times this plus derivative of this. It's not like that. If it were like that, this class would be a lot easier. So that's why it takes so much time for us to get through that material, all right? So applications, there's tons of them. We cannot possibly hit all of the applications in this class, all right? So the ones that we'll look at are, I'll show you just geometrically. The first one is, you know, how does the antiderivative tie into a function? Well, instead of looking at slopes of tangent lines, somehow the antiderivative allows us to find the area underneath a curve. So if someone gives you a curve and they give you an interval, then we can actually compute the area underneath this curve, but it requires that we can find the antiderivative of the function. And why it's like that? Well, again, we'll get to it, all right? And so we'll find the area underneath the curve, or maybe we'll take two curves and we'll figure out where they intersect each other, and we'll find the area between the two curves. Seem reasonable? If you can find the area underneath the curve, you should be able to find the area between two curves. And then we'll say, all right, well what does this represent? Like, what does that area actually mean? And if you go back to Cal 1, you remember when we had this picture and we had the slope of the tangent line, that's supposed to be tangent, then if this was like an object moving, like its position versus time, then the slope of that line was the instantaneous velocity. So there, we could tie meaning to it, right? Well, here we can tie meanings to these areas. And you can have something like, if this is time, and this is the force being applied, so maybe I'm pushing this table across the room, I'm applying a force to it, so at every point in time I have a certain force that I'm applying, then if you kind of add up all the forces, then you can determine, or you can take like a sum of all the forces throughout the entire time I was pushing, and that would be like your work done. So this area can have some physical meaning, your total work, all right? You just have to kind of believe that there's going to be a way to make meaning out of that area, all right? Understand, kind of? Yeah?
That's application?
That would be an application, yes. Now what we're going to do is we're going to do a bunch of geometrical stuff first, and then towards the end we'll do physics, some physics applications, things like, you know, finding centers of mass. If you have some weird, obscure, I don't want to destroy this, but imagine I tear this into some weird shape, like, you know, some weird shape like that. Then where is its center of mass? Well, believe it or not, we can use the antiderivative to determine the center of mass of this. And we can even do it if this is what we call a non-homogeneous lamina, meaning that, you know, if we just get a sheet of paper, we can assume that the density of the paper is the same throughout the paper, because it's all coming out of the same paper mill. You know, if you move from spot to spot on the paper, the density should be the same everywhere. But we know in reality it's not. It's a little different at every point. Do y'all understand what I mean? Like how much wood is packed into that little tiny spot. So even if you give me even if we're faced with a lamina that's not homogeneous, that its density changes throughout the lamina, we can still find its center of mass. But we'll need to use the antiderivative to do that. Okay, we'll also do some things like, imagine taking, I won't do this one, it's going to be a little more complicated, but just imagine taking that area right there, this whole picture, and taking it off, you know, pulling it off the page here, and then just taking that area and letting it swing down and around and come back up. So just kind of wrap it around the x-axis and let it come back up to the top. Then it would swing through three-dimensional space, and it would create this solid object. Can you all kind of see